Okay, so then we're going to see some more applications of second quantization. First is something that I thought promised you like a few weeks ago. Our free electron gas with interactions. We're going to try and see how it looks like in momentum space. Then we're going to talk about the Moore-Tauber transition, which is a really cool model, which is also part of current research, both in all of condensed matter physics. And then we're going to talk about Wick's theorem, which you've also already encountered in class. We're going to see exactly how it works, and if we have time, I also plan on proving the theorem by induction. Okay, so let's go ahead. Let's talk about the free electron gas with interactions. So the total Hamiltonian, this is a general thing for all interacting theories. There is always some part of the Hamiltonian which we know how to deal with. It's a single particle part, so the part of the Hamiltonian that only affects one particle at a time, so the non-interacting part. And then there's, in this case, the electron-electron interaction, which is why it's called a free electron gas. It's the free part with interactions, and this interaction part. And you can always diagonalize the free part, typically momentum space, in which case you just get the typical representation. You have the number operator, and then you have the energy of the kth level. It's usually the momentum doesn't have to be, and there can also be a spin degree of freedom which you have to sum over, and the energy theoretically could also depend on the spin, but it must not. But in this case, let's just deal with a spin zero model, and if there is spin, then just add the spin, the sigmas, and sum over sigma. For simplicity, I won't use spin for this part. Now the interaction Hamiltonian, which is the more interesting part. So what you saw in the lecture is this long and scary expression. So there are two integrals, because you have to sum over two positions of two different particles. And then, as usual, there are creation operators at r and at r prime. Then there's the single particle operator, so the simple interaction itself, which for Coulomb interactions is e squared divided by the distance between the particles. And then you have the annihilation operators, on the other side. So you already know how to read these kind of expressions. You start from the right-hand side. This first operator goes around and detects particles. It goes over all r's because you're summing over r. It detects, is there a particle in r? If the answer is yes, then it goes around and checks all r primes, because you're also summing over r prime. Checks, is there a particle r prime? And if both conditions are fulfilled, then this will be non-zero. Then you can point in the interaction energy with the r and r prime that you found here. And then after you've put in the energy, the contribution to the energy, you put back the particles. Right? So it's a very intuitive way of looking at these expressions. I'm now going to, for the following, just change my notation. Instead of using r and r prime, I'm going to call this r1 and this r2. Just going to make my notation easier in the next step. The next few steps. Right. So now, since the Hamiltonian, or the non-interacting Hamiltonian, is diagonal in k-space, we also want to write interaction in k-space. It will not be diagonal in k-space either, but at least both parts will be in the same basis. Otherwise, it's useless. That will be the start then for the Bayesian theory or Hartree-Fock or whatever. So to do this, we have to use the Fourier transform. So we're just going to plug in the operators. It's the Fourier transform of psi dagger, which is the sum over k. And typically, there's some normalization, which is the square root of the volume. So L is the length of the system, and it's a cubic system. So it's square root of the volume. and then you have plane wave expansion, and there's an AK dagger. And of course, you're summing over k, and this sum over k is over k vector, so you have actually three sums. You're summing over kx, you're summing over ky, and you're summing over kz. It's just shorthand notation. Okay, so what we have to do is take this and plug into here. Right? So our goal is to find the E in K space. Okay, so let's plug it in. Now, the important thing is that when you plug in, right, you have to use it 4 times. You use it once here for side dagger of R1, second time for R2, and then use the Hermitian conjugate for the annihilation operators. So you have to use this 4 times, and then you have to be careful that you don't get confused with different k's, because each sum extends over one exponent and one operator. So I'm going to have to use K1, K2, K3, K4, which are all summation indices, so that I don't get confused between the different operators. Right? This is something that you should know because you've probably done it before, but if you've not, then pay attention. This is important. Excuse me? No. I mean, you have the k vector 4 times. I'll show you what I mean.
Okay.
So what I have to do is the following. I'm going to take this expression and plug in the definition of the transform. So there's an integral dr1, d3r1, integral d3r2. And now, side dagger I replace with the sum here. So there's a sum over k. 1 over L to the 3 halves e to the minus I k dot r1, right? Because it's psi of r1. And a k dagger. And then there's another one, sum over k. 1 over L to the 3 halves e to the minus I k r2. AK dagger. Then I'll call this thing VEE of R. So then or R1 minus R2. So then there's a VEE of R1 minus R2. And then I have to do the same thing again with the complex conjugate of that expression. It's getting long. Sorry. There's a sum over K. R2 AK and another sum over K, 1 over L to the 3 K dot R1 AK hat. Okay, so now what's the problem? This thing doesn't tell me anything at the moment. What I want to do is I want to shift around terms. So for example, I want to move all the sums to the beginning and all the R-dependent parts to the end. But if I now start shifting stuff around, at the moment I still understand that this sum goes up to here. This sum does not include, up to here. It does not include this AK, for example. But it's the same index as here, so I'll get confused. So what I do is I add little indices. This is K1. This is K2. This is K3. And this is K4. So I have 4 different summation indices, right? And 2 integrals. Okay, so keep track. Now I can shift terms around and make it look more comprehensive. So let's take the L's to the beginning, I guess. So we have 1 over 2, well, some of them I'll take to the beginning, some of them I'll leave inside. So there's 1 over 2 L to the third. Then there's an integral d3r1, integral d3r, sorry, I want to do this again. Sorry. That's the whole point. I have the sum over all the k's, k1, k2, K3, and K4. Then I'll put the operators. So there's an A, K1 dagger, A, K2 dagger, A, K3, A, K4. Right, so I'm taking everything that does not depend on R to the beginning. So I've dealt with the L's, so I still have some more L's to deal with in a second. But I've dealt with the A's, now I'm left with exponents. So now I have an integral dr1, integral dr2 divided by L to the third. That's my second half of the L's. And now I have the exponents and I have this function as well. So there's a v e e r1 minus r2. And then there's an, this is r1 and this is r1. So there's an e to the minus I k1 minus k4 r1. And then there's an e to the minus I k2 minus k3 times r2. Okay, you following?
Yep.
Okay, I'm following. Seems to be okay. Okay, now it's starting to look like delta functions, right? That's where I'm heading. But there's a problem. Right? There's no delta function yet, neither on R1 nor R2, because both depend, the potential depends on R1 and R2. But the potential only depends on the difference between R1 and R2, not on R1 and R2 itself. So I'm going to replace R equals R1 minus R2, and then summation of the entire volume, and then I can express everything in terms of this R and only one of the R1 and R2s. So I'm going to express everything in terms of R and R1. Use only R and R1. Should have put this L to the third here. Never mind. So when I do so, I get the, well, the beginning stays the same. So just copy down this. And then you have integral dr1 over L to the third. I'm going to shift these terms around again. So I'm going to first put potential, which now depends only on R without an index. And then I can replace, so I want to get rid of R2, right? So I can write R2 as R1 minus R. And then I can group the R1 part together with this exponent. So first we have here e to the I k2 minus k3 R. And then there's an integral d3 R1 over L to the third times e to the minus I k1 minus k4, and then contributions from here, which is minus k plus k2 minus k3 times R1. Okay? No?
Plus k2.
Plus k, yeah, I said plus k2 and I wrote minus. Plus k2. Okay, that's what I wanted, because now this integral here is a delta function, right? So this is delta k1 plus k2 minus k3 minus k4. And of course, in a second, of course, the meaning of this delta function is that the entire interaction is zero unless, so VEE equals 0 unless this delta function is 1, so unless k1 plus k2 is equal to k3 plus k4. And of course, this is nothing, you know what this is conservation momentum. So we have now, it's imposed mathematically, automatically, that momentum has to be conserved in any interaction, in any Coulomb interaction. Question?
אולי אני לא רואה את זה כרגע, אבל אני צריכה אולי לעשות את זה בדף, אבל כשאני מעבירה DR, להיות כאילו אני לא יכולה פשוט להחליף את DR2 להיות DR, נכון? אז זה כאילו אחרי...
No, the Jacobian is 1. When we use transformation for the integral, the Jacobian is 1 because when we're treating R2 as a variable, as a parameter, and then only R and R1 are variables.
כן, אז צריך להיות כאילו DR פחות, סליחה, DR1 פחות DR, נכון?
No, you don't, because you're replacing, first of all, you're integrating over all space. That's kind of the key here. So you're integrating all space with two variables, so it doesn't really matter which they are, and shifting them doesn't make a change because you're still integrating over all space. And the Jacobian of this transformation is 1, so there's no extra term for the integral. So that's absolutely fine. Just write this explicitly, this is conservation of momentum. Right, so that's the key here. So now let's see how we can use this. So we can use this to replace.
Isn't the Jacobian -1? Because you transfer R.
So you can, yeah, whatever. If it's -1, then you can flip board. I mean,
Okay.
it's infinite space, right?
Never mind.
It doesn't really concern me. Okay, so using this conservation of momentum, I can now go ahead and replace at least one of these indices, right? There's a smart way to do it so that it looks nicer. Basically, we're going to define the exchange of momentum. Why do I say exchange momentum? Notice that K1 itself is not constant. K2 by itself is not constant. The thing that is conserved is K1 plus K2. So these are the two incoming particles and the two outgoing particles. So the sum of the momentum has to be conserved. So one particle can give momentum to the other. And that's what I call momentum exchange. The two particles can exchange momentum in the direction with the condition that in total the momentum is conserved. So the exchange of momentum, which I call Q, is K2 minus K3, which in virtue of conservation is also equal to K4 minus K1. And using this, I can then rewrite the following. And then, so now I can rewrite this potential. So let's do that. So the sum that remains, I'm going to express everything in terms of K3 and K4 and replace K1 and K2 with this. So K2 is Q3 plus Q and K1 is K4 minus Q, right? So I have some of Q as well. And then there's A dagger K4 minus Q, A dagger K3 plus Q. AK3, AK4, and there are hats everywhere, and vectors everywhere. And then I'm left with the integral, and also here, K2 minus K3, that's exactly Q, that's why I chose it this way. There's a D3R e to the IQR times VEE, VEE of R. Right, now it's easy. That's a three-dimensional Fourier transform, and some of you might know what the Fourier transform of 1 over R is. The others can do it at home, because I'm not going to do that now. So you take VEE of Q, that's this thing here, let's see, to this integral, so you have to solve the integral D3R e to the IQR E squared over R. You know how to solve this, right? You use this trick of the z-axis, and this is Q times R times cosine theta. This depends only on R itself, so it's very simple. It's actually one real integral to solve, and it's not even that hard because you have a Jacobian with R squared, so you can wish by parts. So it's simple, and you get E squared divided by Q squared. There you go. Homework. Now let's plug this back into the expression just to obtain the final expression. And I'm also going to rename K3 and K4 to K and K prime, just bringing to standard notation. So we finally get this is equal to E squared over 2L to the third. And summing over K, K prime, and Q. A dagger K minus Q, A dagger K plus Q, 1 over Q squared, A K prime is in here, and AK. Okay, so now look at this expression in K-space. You can now interpret what happens in K-space. We already talked about it, but you see here exactly what happens. These annihilation operators go around and look for a particle at momentum K and momentum K prime. If it has found two such particles that match this description, it puts in the interaction Q, which is just K minus K prime. It puts in the interaction energy, and then puts back two particles, but the two particles that are put back in with different momentum. One of them gains some momentum, the other loses that exact amount of momentum because it's conserved. So whereas in position space, it's gone. Whereas in position space, we annihilate the two particles at R and R prime and put them back at the same place, R and R prime. They didn't jump. In momentum space, they jump during the interaction. So they're annihilated at one point in momentum space and then created at different points in momentum space. Of course, this condition has to be fulfilled, but they jump during the interaction, are annihilated at one point and jump to a different point. So it's not local in K space, but it is local in R space. Space coding means. Okay?
Why does the interaction get smaller when Q is getting larger? When Q increases, the matrix element goes down to 0.
Right.
So does it have any?
Didn't actually think about it. Let me see if I can think of an answer right now. Q is larger momentum, smaller interaction. Larger momentum difference, right? It's a good question. I'll think about it. Let me know if you get an answer. I'm sorry. That is interesting, actually, right?
That's why I asked.
Yeah, I didn't notice it. It's like a known thing, right? That 1 over R Fourier transform is 1 over K squared. That's like a known thing. I don't know what's known. It's like a known thing, right? So I've actually thought about the implication of that. Because it decays faster in momentum space than it does in R space. Like that is, it's interesting, but I cannot give you a hand-waving argument for this to think about it. Okay, any other questions about? Okay, so this is something that is done very typically. It's the kind of calculation, right? It's all based on switching indices, finding delta functions, and then getting rid of integrals and sums as much as you can. And you have an example, a simpler example with the density operator in your homework. Okay, next. Let's talk about our first example of a main body system. So we're going to consider fermions, and these fermions are going to sit in a double well potential. And since they're fermions, they are spin 1/2 particles, or we're going to use spin 1/2 fermions. So the number of particles, number of fermions that you can put in the system is either 0, 1, 2, 3, or 4. The maximum is 4 because you have on the left side an up and a down, and on the right side an up and a down. I think of this as a tight binding model with 2 sites. That is site number 1. This is site number 2. In the second right hand Hamiltonian. So the maximum amount of particles is an up particle here and a down particle here, and the same thing over here. But of course, there could be less. There could also be 0 particles in the system. We know how to create and annihilate them, but that's the maximum you can have. Now, the Hamiltonian, I'm going to write it out in its full beauty. The Hamiltonian that we're going to discuss for the next half hour or so is the so-called Hubbard Hamiltonian, which is what you know from solid-state physics as the tight binding model, but now it's tight binding with more than one particle. In solid-state physics, it was only one particle. Diagonalize it, you found omega of k, so the dispersion relation, but it was only for a single electron. But you see in a moment I'll also add an interaction term that was not present in your solid-state studies. So let me get there. So there's this term, there's A1 dagger up, A2 up, plus A2 dagger down, A1 down, plus A1 down, dagger A2 down. These are all the hopping terms. So these are your two sides. And you have, say, a particle here with spin up, and you want to move it over here. No colors, yay. So we're going to move it over here. So the first operator here does exactly that, right? This is 1 and 2. So the first term in the Hamiltonian creates a particle over here and annihilates an up particle here. So this is A2 up dagger, A1 up, right? And you have 4 such terms. The up particle can hop, down particle can hop, and you can hop from 2 to 1. So 4 terms in total. And then the second part of the Hamiltonian is the on-site interaction. So only particles that are on the same side can interact. So it's U, which is the interaction energy, and then you have to count the up particles and count the down particles on each side. I'm missing a 1. 1 up and 1 down, plus N2 up and 2 down. Right, and N is A dagger A. So if you use these pictures, then if you have 2 particles in the same side, one of them is up and one of them is down, and say 0 in the other, then here there's an on-site interaction. There's positive interaction energy U.
Why is the multiplication between N1 up and N1 down?
Because this number operator can be either 0 or 1. Right, the fermions. So if there are 2 particles on the same side, you want to get U. So in this case, this is 1 times 1. But if you have the case where you have 1 particle and 1 particle here, you want to get 0. So that'll only work if you multiply by with them.
What is U?
If you look at this state, where you have, say, an up particle here, and say an up particle here. So what does this term contribute? 0, right? Why does it contribute 0? Because the downs are all, right, N1 down and N2 down are 0. That's why it's called on-site interaction. It only contributes to the energy if 2 particles are on the same side. Neighboring sites do not interact. They can hop from one to the other, but if this particle hops, well, it can't because it's up, but if, say, it's down, right, so this is a down particle, and it hops over here, then it's negative energy, so it might favor hopping here, but there's a repulsive on-site energy, right? It's positive, so it might not be worth hopping over here. It depends on what's larger, where it gains more energy. Let's say if you're looking for the ground state, or it could be an excited state to go over there, right? So these are the things you have to think about. That wasn't correct. So what happens if this system has 4 particles in it? If the system has 4 particles in it, which means that it is fully filled as much as it can, In that case, the system is an insulator. What do I mean by insulator? I mean that the fermions, let's call them electrons, cannot move. The Hopf intern cannot do anything because all sides are filled to the top. So what you know from solid state physics as a filled band, right? You could have many such bands, and this would be a filled band. So it would be and a filled band is an insulator, does not contribute to conduction. And the same thing happens for zero particles. Obviously, zero particles cannot move anywhere. So for n equals 0 and n equals 4, this system is an insulator. N equals 0 and n equals 4, the system is an insulator. But if you want to extend it to like the infinite case where this is not just two wells but a lattice, then either 0 or n equals 2 times the side, so full, will be an insulator. But any other number in between can conduct because you can hop from one term to the other. So for any other n, you would also be an insulator. Except, there's one special case. So this is what we call a band insulator. There's one special case, and that's the case, so else is a conductor. And there's a special case, and that's the one we're going to discuss today. The special case is when n equals to 2, and we're in the limit where u is much larger than t. So the on-site interaction is very strong, and the tunneling or the hopping rate is very small. In this case, and I will show this to you, or actually hand waving always are enough, but I'll also show it. You'll see that the ground state is to have one particle here. We'll talk about the spin state later. But one particle here and one particle here, and this particle does not want to go here because the on-site interaction is so large, it's just not worth it. So the ground state of n equals 2, the ground state is an insulator, and this is something that is called a Mott insulator. After the inventor or discoverer of Mott. Yeah, so the condition is that the on-site interaction is much, much larger than the hopping term. In this case, a half-filled band, right, is something you don't know from solid-state physics. A half-filled band can be insulating. Okay, and this works. This has been also verified experimentally. It's not just a mathematical model; it actually works, and it's current research works with this not with two sides, not in one dimension, but in 2 dimensions as well. This is a very interesting system.
What about the case that n equals 2 and you have the same spin at both sides?
Right, so we'll now see what happens with the spin. Okay, let's talk about our system and we'll see what happens to the spin in this ground state.
But
so we're going to the ground state, right? So ground state means that you have to cool the energy or the temperature below the hopping or interaction. Otherwise, the energy will take to an excited state, and you could become a conductor. We're talking specifically about the ground state. Remember that in solid-state physics, room temperature is usually the ground state. Right. So we're going to talk about what happens to the spins and the magnetic interactions in a moment. Okay. Okay. So now we're going to talk about this system with n equals 2. So this is the case we're going to deal with. Let's look at the possible states that we can be in. So there are 6 possible states that the system can be in if you have 2 particles. 2 states are called spin polarized states, meaning that all spins point in the same direction. So either up or down. You could have 2 single occupancy states. Single occupancy. But not spin polarized. So that's 1 up and 1 down, or the other way around. The first one down and the second one up. And then there are states which are double occupancy states, which is the case where one well has 2 particles and the other well has 0 particles, so an up and a down, or an up and a down here. These are the 4 possible states. I will call these states, so this I'll call P1, and it's equal to A1 dagger, A2 dagger on the vacuum. This I'll call P2, and you can write an equivalent expression. This will be S1, color. This will be S1, which is A1 up, dagger, A2 down, dagger 0. This will be S2. This will be D1. And this will be D2. The letter code is P for polarized, S for single, and D for double. In case you're wondering.
Not SPD.
רגע, והדאבל, סליחה, הדאבל, אפילו שהוא מלא כאילו אחד, אבל יש לו מקום לקפוץ לשני, אז הוא מוליד?
So right now, you're asking, this would be this is not the multitrader. What I'm doing right now, this was like motivation, it's what's going to happen. Now let's analyze the system. So now I basically wrote down my Hilbert space. I wrote down the possible states that this system can take if I define the 2 sites and 2 particles. Right? There are no other possible states. This is all of Hilbert space. So now I defined my Hilbert space. That's usually the first thing you do when you get a system, right? The Hilbert space, and then diagonalize, so on.
הגראונד סטייט שלך זה שאין שום דבר, פשוט כאילו ואקום? הגראונד סטייט שלך זה...
Yeah, ground state means 0 particles. The 0, the vacuum state. It's not the ground state, it's the vacuum state. That's just how you create the particles. Okay, so now let's first talk about the spin polarized states. The special thing about the spin polarized states is that they have 0 energy, right? Now, before even taking the limit where U is larger than T, let's forget about the limit. If you look at the Hamiltonian, you might think that this should be the ground state, right? Because it's 0 energy. Why is it 0 energy? Because it has no contributions from this term and no contributions from this term. Right? You look at the terms, all of them give you 0 because there's no state where both operators give a non-zero value. Right? But this is wrong. This is not the ground state, and that's because other states can take advantage of the hopping term, and this is negative energy. Now, if you already look forward at the limit, you can understand that this must be the main contribution to the ground state, the single occupancy states, because if U is much larger than T, then obviously the ones that can profit most from T and have 0 U will be the ground state. In fact, we will see that these 2 states, or a superposition of these 2 states, will be the main contribution to the ground state, but we're going to do it in a mathematical way as well. This is, without even doing anything, we already see that this is what should happen.
What are we trying to find? Okay, with this is our case of the problem, so...
What are we trying to what?
מה אנחנו מחפשים? מה אנחנו רוצים למצוא?
Right, so what we're going to do is we want to find basically the Hamiltonian of the ground state. I'll show you in a second what the procedure is, and I hope it'll be clear. So first of all, motivate that this will probably be the main occupant, the main contribution to the ground state. We can also limit ourselves. Okay, let's take a step back. We've realized that this state, the polarized states, okay, let's think about it differently. These spin polarized states, they are eigenstates of the Hamiltonian, right? With eigenvalue 0. These 2 states, or these 4 states, are not eigenstates of the Hamiltonian, right? So in total, you need 6 states, 6 eigenstates. This is 1, this is 2. The other 4 have to be superpositions of these 4 states. And I've motivated that the energy of at least one of these states could be lower than 0. So the ground state is going to be a superposition of these 4 states. Right? Following so far? So this is a subspace, and we're going to look at the Hamiltonian in this subspace of the single and double occupancy states. And the procedure that we're going to do is the following. First of all, we're going to concentrate in the limit where u is much larger than t, and so we're going to treat the hopping as a perturbation of the interaction, right? Because it's much smaller. And then, so first we're going to do a canonical transformation. Canonical transformation, if you remember from analytical mechanics, it's a transformation of the variables of the equation of motion, which leave, or of the Lagrangian, of the Hamiltonian, whatever, which leaves the equation of motion invariant. Doesn't change them at all. So you can always do this transformation without changing the physics of the system. And it could be useful because you might be able to write the Hamiltonian in an easier way, easier for mathematically, but it still contains the same physics. So I'm going to use, first of all, a canonical transformation to transfer h to h prime. Then, after doing that, we're going to project h prime into the subspace of the single occupancy states, because we already understand that the ground state must compose mainly these 2 states. So in the second step, we're going to project h prime into the SI subspace. Not the total subspace. We're going to look at h prime in this subspace of the 4 states, but then we're going to project it into this subspace. And the goal will be, I'll tell you what the solution will be, you will see that the Hamiltonian that we then get will have anti-ferromagnetic order. So we will get a Hamiltonian to which we know that the ground state is anti-ferromagnetic. You will know that. We'll see the Hamiltonian and say, I remember this. Maybe an Ising model with positive J, which you should know that the ground state is anti-ferromagnetic. Wait a second, and that way we'll see basically that although the Hamiltonian does not include any magnetic interaction, it includes only the on-site Coulomb interaction, right? We don't mix different spins. So there's no spin interaction here, but it still causes the ground state to have a magnetic order, which is pretty nice. So if you can, first you can try writing out the Hamiltonian, right? This Hamiltonian is a 6 by 6 matrix. You can try writing it out. You will notice that if you look at the matrix elements between different states, so take states, try to write them, alpha, h, beta, where alpha and beta could be any of these 6 states. Then the matrix element between this state and any of the other states is 0. But the matrix element between this state and this state, for instance, is non-zero because you get a contribution with hopping, right? So you use the first 2 hopping terms, this one and this one, right, will change these 2 states. So the matrix element between these 2 terms is minus 2t. So you have an off-diagonal term. But in the rows of the piece, there will be no off-diagonal terms. You can just apply the Hamiltonian to the states, you'll see it right away. That's the easiest way to do it. Of course, one way to solve this problem is actually to do exactly that. Write down the Hamiltonian, right? 6 by 6 matrix, or after you've identified that these are eigenstates, you can use the subspace and make it a 4 by 4 matrix, because the first 2 lines are already diagonal, so you have a block diagonal matrix basically, and you'll have to diagonalize a 4 by 4 term matrix, which is not that difficult. It's only 4 by 4. You can use some numerical computer if you want to, and you can do that. But in general, if you now want to think about an infinite lattice or many lattice sites or even a two-dimensional lattice, then that becomes impractical. And the procedure that I'm going to present for the small system also works for larger systems, can be generalized quite easily. So the result that we're going to obtain is going to be general also for larger systems, which is why we're doing this. Question before we start?
שאלה על ה-contribution, כאילו, מה זאת אומרת contribution to the ground state? כאילו, אתה מתחיל מזה ש-ground state הוא אפס, או שאני פשוט אומרת שהמקום עם האנרגיה הכי נמוכה הוא אפס?
Yeah, the ground state is the state with the lowest energy, by definition, right?
לא הוואקום.
No, because I have n equals 2, I'm defining that I have n equals 2 particles. The number of particles is unchanged. So, given 2 sites and 2 particles, these are the 6 possible states. And I want to find the ground states. I want to find the eigenstate with the minimal energy. But minimal is not 0, obviously. Minimal could be negative, since there's a minus t, right? So that minus, so the states that profit the most from minus t are these 2 states. And this can also profit from minus t, but it also has the u, right? The Onto interaction. So if u is much larger than t, then obviously this will be positive. And this is the only term that could be negative. So you'd expect these terms to be eigenstates, which is why we're going to eventually project into that space. You can do so. What you can do, I've written this in one of the footnotes. You can actually diagonalize this 4x4 matrix, and you'll see at the ground state, the more you take the limit of u larger than t, you will see that the coefficients of these 2 states become much larger than the coefficients of these 2 states. So you can look at it in that way as well. But of course, that's the undergraduate way to look at it. Now let's look at it in the graduate way.
Yeah, probably don't think the Hamiltonian couples the 2 S states. I think it couples the S states to the D states.
No, because you have 4 terms there. So
yeah,
they are coupled by minus t, and this measurement is minus 2t.
But there isn't any term that couples directly.
No, but there's a sum.
Yeah, and one couples S1 to D1, and the other couples S1 to D2, and again.
No, there's a term, right, which is A2 up, A1 up dagger, and then there's a term A1. Hope I think is correct. Dagger. A2, I think this term is non-zero between these 2 states, right? Because you have...
No.
The first term moves this here.
That becomes a D1, D2.
Sorry, I need downs here.
Okay.
Right? So this term
you'll get a
moves this into this, right?
No, you'll get a superposition of D1 and D2.
Right, I'm moving the up.
But it's not addition. It's not.
It's the other way around. It's up and down, opposite, rather way around. But whatever.
No, but you aren't actually multiplying these 4 operators. You're adding, so you have a superposition of D1 and D2.
Still got a superposition.
No, but it isn't coupled to S2 directly. That's what I'm.
Okay. In any case, the ground state must be a superposition of these 4 states, right? Okay. That's basically what I'm trying to say. So let's go ahead. Yeah, Wick's theorem is going to have to wait. So let's go ahead and do this. Right, so first of all, let's do this quick. We're going to have to define projection operators. So projection operators in second quantization, we need 2 projection operators. One of them which projects onto the S subspace, so just the 2 singly occupied states. They have to act on the SI states to return SI, and when they act on the D states, they have to return 0. By definition, that's what a projection operator does. So it acts on any random state, it will project it onto the S subspace. So you can verify that PS equals 1/2 Ni2 minus Ni will do exactly that, where I've defined Ni to be just a total number of particles without respect to the spin. So if you write your states in the bases, the Fock spaces, where you write them as N1 up, and then number of N1 down, and the number of N2 up, and N2 down. If you use this as your basis, where this together is N1 and this together is N2, right, it's just Fock basis, so the state S1 is in this basis 1010, sorry, 1001, right, using this Fock basis. And if you now apply PS on this, on S1, you can verify that you get S1 as it is. And if you look at, for example, the D1 state, which is in this basis 1100, so if you then apply the PS onto D1, then you'll get 0 because of the 2 minus N1.
יש שם שווה בשורה השלישית?
Yes, this is the projection operator. It'll project any state which can be written as a superposition of S1, S2, D1, and D2. It'll project it into the S basis. So that's that, and then you can also define the same kind of operator for the D states, and you'll have time to play around with these states in your homework. That's life. Okay, now comes an important step, which is a little confusing. So what we're going to do is define a fancy operator, which I'm going to call F. It's a very interesting name. And it's equal to 1 over T times U. This is the constants from the Hamiltonian. And then it's PSHTPD minus PDHTPS. What are these terms? So the PS and PD are projection operators into S and D subspace, and HT is the part of the Hamiltonian that includes the hopping term. In the same way, also call HU the part that includes the interaction term. So the total Hamiltonian is just HT plus HU, right? It's obvious which term belongs where, right? Why am I going to find this operator? It's a little weird. Also, you'll experiment with this as well in your homework. In particular, you can show that the commutator between this new operator and the interaction part of the Hamiltonian is equal to 1 over T times HT. So I'm not going to prove it. It's quite a long calculation. But you can show that this operator has this property. And this is going to be helpful in a bit, so note this. Let's start out of the blue. Just accept that this operator has this commutator. You can verify it later on, and let's just use it, okay? It's a fact. And the second fact is the canonical transformation. I'm not going to prove that it's a canonical transformation, but you can show that this transformation leaves the equations of motion invariant. So you can prove that this is a canonical transformation using the definitions of canonical transformations, and I refer you to your course on analytical mechanics in case you remember, and if not, then don't remember. But this is a canonical transformation, and it leaves the equations of motion invariant, so you can do this without changing the system. Okay? So 2 facts, right? Fact number 1, commutator. Fact number 2, the same F has this property. True, but Strasbourg didn't.
But what?
But Strasbourg didn't. So you're in the wrong year. My problem. if you open up Goldstein, then
No, it's key.
if you open up Goldstein, then you can verify this is true. Someone remembers this? No one, right? Yeah, I don't either, but apparently it's true.
That's related to the Heisenberg picture or Hamiltonian or something.
Hmm?
Isn't that related to the Heisenberg picture or mixing up?
No, there's no I here, right? And this t is not time, it's the Hopkin coefficient. It's not a variable either. So it's not the Heisenberg picture, but it looks similar. And actually the way we're going to deal with this is very similar. What should we going to do now? First of all, you know how to deal with operators in exponents. You expand in Taylor series. Now the good thing is that we're doing a perturbative treatment where, guess what? T is a small parameter. And guess what? T is an exponent. So when we open this into a Taylor series, we'll be able to neglect higher terms. Okay, so it's starting to make sense, right? Yay, so cool. So when you expand this in a Taylor series, and I'll skip like one line of algebra. Basically, I'll keep up to second order in T. And the reason I'm going to keep up to second order in T is because the first order in T, as you will see shortly, is going to cancel. Actually, to prove this, I think is a homework in Quantum Mechanics 1. It is now, because I'm teaching it and I give it the homework in Quantum Mechanics 1. But for those who didn't have this as a homework, you can prove this property. It's basically open this up as a Taylor series, you get 1 minus TF plus TF squared over 2, and the same thing over here with plus signs, and then the minus sign here and the plus sign to here, give the commutator, and so on and so forth. And now the good thing is that we can now use, so we can now write this H as HT plus HU, right? We can use this, and then we're going to use this. So doing this, we get here 3 terms, not 3 terms, many terms. We get HU plus HT minus, and then we have 2 commutators. Just a commutator of F with HU, and the commutator with F and HT. And then also here I get the same thing. But remember, I'm keeping only second order terms, and HT has a T in it. So if I put here HT, this becomes a third order term. Only the contribution with HU is a second order term. So this will disappear. This goes like T, so it'll cancel because I'm removing all T to the third and above. Right. So I have to keep one term here, which is T squared over 2 HU. And now comes the cool part, where we use this property. What's this property do? So the commutator with F and U and HU is 1 over T HT. So this thing becomes minus HT. That's useful. Right? And it means that this thing here becomes also 1 over T HU, and then you can cancel one of the T's here. HT. Oh, you're following. Awesome. And I can cancel the 2 over here, and then you have minus T, this commutator, plus T over 2, the same commutator. So you get minus T over 2. Right? So in total, you get that H prime is equal to HU minus T over 2 FHT. Much nicer way to write the Hamiltonian. Okay? Go ahead. What's next? Okay, next we have to evaluate this commutator, which we'll do in a second, and then we have to project this into the S subspace. So the next 2 steps will be to commute the commutator, and then we'll have to project into the subspace.
Why are we doing all this and not just diagonalize the 4x4 matrix?
Because if in the homework I give you an 104 by 104 matrix, you're not going to diagonalize it. Not because you don't want to, but because your computer will have the power before it's done, right? Actually, 100 by 100 you'll probably do, but if it's 10,000 by 10,000, you have 10,000 squared elements, I wouldn't be so sure. It's,
אני רוצה לעבור למידת מרחב שבו אסים הם הוקטורים הפנימיים שלי.
no, so we're not going to actually write the eigenstates, we're going to write the Hamiltonian. The effective Hamiltonian, maybe I should stress this, it's a good point. Our goal is to write an effective Hamiltonian, which is true in the limit u much larger than t, and in the limit of the ground state, so cold temperatures. Okay, this is an important thing that repeats itself very often in solid state systems. We're usually interested in solid state systems in the ground state. So we're writing an effective Hamiltonian that is correct in the ground state, not for excitations. We're losing some of the physics. Right? We're losing the excitation spectrum. We'll be able to deal with that later by including higher order terms of T. But at the moment, we're interested in the lowest order terms, both in T and in temperature, in order to get an effective Hamiltonian fully ground state.
ברגע שהפעלת את PS על T, קיבלת 0, זה היה כאילו מכוון שאני אתעלם מהמצבים של T, נכון? שלהם יש אנרגיה גבוהה.
Well, you're asking about why PS times D equals 0? This is by definition, because it's the projection onto the S subspace. PD, on the other hand, if you apply on DI, you'll get DI, and if you apply PD on the SI states, then you'll get 0, right? That's by definition the projection operator. And then
אתה בעצם מלחסן רק את המצבים של S. אני מנסה להבין כאילו...
I'm not diagonalizing anything. I'm not diagonalizing the system. So this is not diagonalization. I'm taking the Hamiltonian, which at this point still includes all the spectrum of high energies as well. Up till now I've only neglected high order T, but not, I haven't gone to low, to the ground state yet. Now I say, okay, let's assume that the system's in the ground state. Let's see what the Hamiltonian looks like in the ground state. Okay, that's what we're trying to do. And because in the ground state, I know that these states, the S states, are going to be the relevant states, I'm projecting into that subspace. So I'm forcing the Hamiltonian to be such that I can have only one particle per site. Right? Because this Hamiltonian still includes 2 particles per site. As soon as I do this, I'm forbidding it. I'm imposing this on the system. No, so we said we're not even looking at P because they're definitely on the ground state. They're, first of all, they're already eigenstates of the original Hamiltonian. Yeah. So we then already put them aside. Now we know these are eigenstates. Let's look for the other eigenstates, which are a superposition of S and D states, and then we realize that the ground state must be one of these other 4, right? Because at least one of them can have lower energy than 0. Right? That's the procedure. So after you compute this commutator and you do this, I think I'll just jump to the last line because I want to do Wick's theorem as well. It's basically algebra from here. Okay, it's algebra, and you're going to have to use. That's an important point. You're going to have to use the definition of spin operators that we used last week. So you have to use that the spin operators are these sums over alpha and beta. What was it? A dagger alpha, sigma I, alpha beta, A beta. So you're going to have to use these definitions from last week, and then you'll realize that these hopping terms can be written as spin operators. And then when you do this, so bottom line, again, there's some algebra here, and part of it is in your homework, so you have no choice to do it, and some of it is not your homework, but you may do it because you love doing algebra. And the bottom line of this calculation is that you get J, which is some constant, which I'll define in a second, minus a quarter, and J is equal to some combination of these states, 4t squared over u. So basically you'll find that your total Hamiltonian, right, you can forget about this quarter, it's just a constant, it's the shift in energy, I don't care about that. So the total Hamiltonian, the effective Hamiltonian for the ground state, maybe I should write this down, this is an effective Hamiltonian for the ground state. The Hamiltonian is a spin interaction, and if you want to scale this up in general, so for many sites, not just two sites, then the Hamiltonian becomes some J sum over Nm, closest neighbors, right? Only S1 and S2 interact. You can show this in a more elaborate calculation, but you get this Hamiltonian. And now I remind you of what you should have learned in previous lectures. You might be used to seeing this with minus here, in which case you know that's the Ising model, and you know there's a phase transition into a ferromagnetic phase in the ground state. But if there's no minus here, and J is a positive number, then this thing has anti-ferromagnetic ordering in the ground state. So this thing is anti-ferromagnetic. So you can show that this Hubbard model, so it's the first unintuitive thing about it is that it's an insulator, although it's only half filled band. And the second unintuitive thing is that it gets you get an anti-ferromagnetic order in the ground state. So it's been up, down, and so on. Which is pretty cool. So if you didn't follow all of the algebra steps, that's okay. You'll be able to sit in it later. I don't expect everything to be clear because it really isn't that simple. Just know the main steps. So one of the steps, and this is something you couldn't guess, something you just have to, this whole calculation was done in a way that we already know where we're going. We know what the solution is. So let's just, copy what someone else did. And he probably guessed a million times until he got it right, right? But we know where we're going, so we can make the right guesses from the beginning. But the first thing is this canonical transformation. So you can put the Hamiltonian in a nicer way, right? Because this thing is easier to compute than the original Hamiltonian that we had. And it allows us to do the perturbative expansion in T and neglect higher orders. Which shows F in a way that the first order terms will cancel, right? This is the second order in T. Because the HT is linear in T, so there's a T squared here actually. So it's the second order in T, and HU is 0th order. And then the second part is, of course, realizing that you're actually looking at spin operators, and you get the antiferromagnetic order.
לא צריך להיות שם ב-PHP, אחד מהם דגל או משהו,
No.
מה זה עושה בכלל?
It's projection. Right, from both ends. So well, the dagger is the same thing, right? It's the thing about projection operators. It's a remission operator, so okay, last topic for today. Something a little bit simpler, mathematically speaking. Wick's theorem. So let's take 15 to 20 minutes to talk about Wick's theorem, and so forget about this complicated stuff for the moment. We'll get back to it when you start solving the homework. Okay, let's do Wick's theorem. Let's consider for the moment just bosons, but you can do the same thing for fermions as well. I'm just going to focus on bosons at the moment, so I don't have to run after minus signs, and it'll make the discussion a little easier. So let's look at an example where we have a product of 4 operators, and the product I would like to look at is following. I'll just choose some random example. So I'm first going to motivate what we're going to do, and then I'm going to present Wick's theorem, then we're going to use it and show that it works, and then if we have time, we're going to prove it by induction. But that'll probably not happen today. But the main thing is that we understand how to use it. So we have, this is an example, right? So we have this product operator. We now define what I call normal order of A, B, C, D of this operator. And sometimes people also write, like Fat writes this with the double points, but I prefer to write N, but it's just a convention. And this is by definition distinct normal order. So it's all the daggers in the beginning, L and M, and then the non-daggers, K and N. Now let's see what we have to do to the state in order to bring it into the normal ordered state. What has to be done? So this is an easy thing to do. All we have to do is use the commutators, the so-called Heisenberg algebra. So we have A, K, A, L dagger, A, M dagger, A, N. Now we can write this as the commutator of A, K, A, L dagger, A, M dagger, A, N, plus A, L dagger, A, K, A dagger, M, A, N. Okay, so I've switched the order between the first two operators. And when I switch the order, I get this one, but then I have to use a commutator, right? So if you open up this commutator, you'll see, I'll just get this back, right? Quite straightforward. And doing this once more, so the first term now is in normal order, because this is a number, so this one is in normal order, so we can leave that as it is. And in the second term, we now have to invert the K and the M in order for it to be in normal order. So we get another commutator. There's an A, L dagger, A, K, A, M dagger, A, N. And then we get the last term, which is the normal ordered operator. So this thing can be written as N, A, L dagger, A, M dagger, A, K, A, M. Doesn't do anything, right? Normal order puts this in normal order, which is exactly equal to this. So that is what add the normal order sign. Not doing anything. Okay, now we'll define the contractor. You will see in a second where I'm going with this. So the contractor between two operators is defined as the difference between the two operators and its normal order. This is the definition of the symbol. Every time I write this symbol, what I mean is AB minus the normal order of AB. And of course, you can see that this is equal to 0 if AB is in normal order. And it's equal to the commutator of AB if not. This means that this expression can be rewritten simply by I can replace Right, this thing by AKAL dagger contracted, right? Because that's what it is by definition. And this thing is AKAM dagger contracted. Right, so I defined some weird-looking symbol, and now I'm using the weird-looking symbol to write my expression, which had, square brackets. It now has a square bracket on top. Didn't do anything, right? It's just a new notation.
Why is it correct again, please?
Right, next question. That's how I'm defining it. I'm defining A, B with the contractor is equal to the commutator of A and B. So I can replace the commutator by the contractor. It means the same thing.
Or 0?
Well, this could be equal to 0 or to delta or to 700. It doesn't matter. I'm defining that, the contractor is either the commutator or 0. I could add here terms with contractors to equal to 0. Right? I'm not doing anything. Now comes the important point. I can now rewrite this. So I can take this normal order sign and put it in the beginning and put all these terms inside of the normal order operator, and then write these terms in the original order. Actually, what I wanted to write here is not what I meant. What I meant to do here is to write that this is equal to the normal order of what we had in the beginning. AK, AL dagger, AN dagger, AN. Right? That's the important point, right? This is the normal order of this term. And now I'm going to write all terms from that order. So this is equal to AK, AL dagger, AM dagger, AN contracted, when I've contracted K and L. So this plus AK, AL dagger, AM dagger, AN, where I've contracted K and M. So that's this, right? Plus what we had in the beginning. Plus AKAL dagger AM dagger AN. Closed normal order. So these two expressions are equal to each other because these blue terms are all in normal order, and this means take the normal order of what's inside the bracket, so it's equal to the blue terms. Right? But now I have written all the terms in the same order as I had them in the beginning, which is not the normal order. Put the symbol around it to tell you, by the way, I mean normal order, but it's very formal. Right? Seriously? It's all notation. Okay, I haven't done anything. It's all notation. Right? So up to everything that is in blue is obvious, right? Everything in blue is fine. All the rest is notation. Okay, because Wick is a weirdo and he invented this weird notation. Okay, but it's very helpful. And all I'm doing between here and all these other fancy colors, it's just notation. Okay, so if you want to open up, let's go the opposite way. Right, if you want to open up these brackets, right, then this is just a number. Let's say it's equal to 1. Okay, who cares? It's delta KL. Okay. So this is the number delta KL, which you can write as the commutator of KL. And then you have to move your terms around so that this term will be, that the rest will be in normal order. So that will give you this term. I'm starting here, right?
רגע, שנייה, אני בכלל תקועה בזה שאם אני שמה את הגג הזה על AK ו-AL דגר, אז...
I mean commutator.
כן, אני מבינה את זה, אבל הם לא בנורמל אורדר.
Right.
זה לא כבר 0.
What? They're not in normal order, which is why it's common. If they are in normal order, is in normal order.
סבבה. דבר של סבבה. עכשיו למה יש את ה-N בחוץ על ה-L של ה...
Right, because let's go the opposite way, okay? Let's go from here to there. So I want to rewrite this term using normal order. What I mean is this. I take the normal order of the first term, but this is a commutator, right? So this is the commutator AKAL dagger, right? That's what it means. And then the normal order of whatever's left. So that's AM dagger AN.
כמספר. בסדר.
Right? Now, here's on the second term. What do I have to do to rewrite this? So first of all, let's just look at this contractor. It means take the commutator between AK and AM dagger, right? And now the remaining terms have to be written in normal order. So all daggers to the left and all the others to the right. So this is AL dagger, AM, this should be an N, right? This is exactly this term. Remember, the commutator is a number, you can shift it around. And then the last term, this in normal order, is this term. So this black notation is equivalent to this blue notation. But this is in the language that we all understand, and this is in the language that we're now learning. Right? But it means exactly the same thing. Following? Perfect. Okay. Yeah, the commutator is a number.
אני לא מבין, למה הכל תחת normal order? כאילו, זה לא, כי you started from a state.
Right, but this thing is equal to the normal order of these three terms. I've added the commutators to make it normal order, right?
Yeah, but why would you specifically choose this? I mean, for example, take the third component in the normal order bracket. You can commute it however you want.
Why? No, I can't. That's the whole point.
Inside the normal order, you can commute it because the normal
the
order,
daggers between themselves?
for example,
So who cares? If you can, as long as they're bosons and you can just do that, who cares? Right?
I mean, is there any meaning to the specific
So
order?
usually what you would do is you would choose some order in your Fock states, and say you'd order your Fock states, right? You have the numbers of the occupations, and you put the lowest energy, so the lowest, like think of an infinite potential well, for example. So you put the ground state first, and the first excited state second, and so on, and you choose by convention some order. But of course you're free to choose that convention. And it makes sense to choose here in the order the same convention that you chose back there. But it's a convention, it doesn't really matter. Like you say, it doesn't matter, so who cares? Right? Define your convention at the beginning of the paper. Go ahead with it.
Okay, I just didn't understand why to use n over all this. You could just keep it.
I could. So until now, what I have done seems stupid to do, right?
Okay, I'll see what you.
And now I'm going to state Wick's theorem, and then I'm going to solve this example using Wick's theorem, and I'll show you that you get exactly this term, or this term. So I'm just going to show you that it works. That's my goal. So let's state Wick's theorem. That theorem. So we now have a lot of operators, A, B, and so on until Z. It's a product of however many you want. Of course, there are only 26 or so letters in the alphabet, but you know, go ahead and put in like Greek letters in the middle. So it's just a number of operators, and this is equal to the normal order of this product of operators plus what I call all contractions. What do I mean by all contractions? What I mean is this. All contractions mean I have to do this one by one. So A, B, C, D, I look at an example of 4 operators, is equal to the normal order of A, B, C, D itself, right? And then all contractions. Now there are 2 ways of contracting. I can contract 1 pair at a time or 2 pairs at a time. So there's 6 options to choose pairs. So I can do A, B, C, D and contract A and B. I can do A, B, C, D and contract A and C. I can do, and this goes on for a while. I can contract A and D. That's 3 of the 6 terms. And then there's an A, B, C, D where I can contract B and D. And then I can do A, B, C, D. No, let's do first B and C. Just get some normal order. And then B and D. And then the last one is C and D. Right? These are all pairs. But I'm not done yet, because all contractions also includes contracting 2 pairs. So So this is, I also have to add A, B, C, D, where I contract A and B with C and D. Right? And there are two more terms like this. I can subtract A and C and B and D, and I have to use this extra height to use this notation. And you contract C and D and C and A and D. So this term is the simple term, that's the first one. And all the other 9 terms is what I mean by all contractions. Start with the pairs, go to 2 pairs, if you have more, 3 pairs, 4 pairs, and so on and so forth. So you get a lot of terms. Okay, that's what the theorem tells you to do. And it tells you that this ABCD is equal to the normal order of all of this. Now why is this useful? These terms in the last line is what I call fully contracted. They're fully contracted terms because there are no more operators left. Remember that the contraction is just the commutator. It's either 0 or the commutator itself, right? So there are only numbers. There are no more operators here, right? All of the other terms in this expansion have on the right-hand side a annihilation operator. So if you now put this operator and take its vacuum expectation value, then the only ones that will survive are the fully contracted terms. All the other ones have an annihilation operator on the right or a creation operator on the left, which is all equal to 0, right? The same way that A0 is equal to 0, 0, a dagger is also equal to 0, right?
But
So,
A with D, כשיש לך את A ו-D כאילו שמחוברים, B-C דווקא הם מסתדרים, זה לא צפס.
No, this is also here, because the contractor is a number, and then BC, you have to order in such a way that all the daggers are on the left, and all the non-daggers on the right.
But
So this will always kill you.
You contract all the daggers, or you can contract all the non-daggers for the annihilation, and then you have only daggers on the right. It's not possible?
It's possible to have only daggers. It's possible that both...
For example, there, A and D.
Right, so it's possible that both A and D are daggers, but then this will kill you. It's possible that both are non-daggers, and then this will kill you.
When you write normal order of the sum, do you mean the sum of normal orders? And
It's the same thing.
is it?
Of course.
Okay.
אם כולם דגל.
So this will kill you.
אבל זה רק שאני... רגע.
Because remember that the contractor is a number, so you can move it around.
כן, זה בסדר.
So if they're all daggers, or if they're all non-daggers, or if they're 50-50, or whatever ratio you want, either one of these will always be the case. So in all of the expressions, except for the fully contracted case, where you have only numbers, they will all be killed. So this expectation value will be equal to the sum of all fully contracted terms.
אוקיי, expectation, בסדר. רק עליו.
Yeah, the expectation value. That's why this is useful. So Wick's theorem is only useful if you're trying to evaluate vacuum expectation values, which we'll start doing in a bit. Maybe you've done it already. But this is what perturbation theory is based on. So if you want to evaluate such expectation value, do this calculation. Actually, you don't even have to do all of it. All you have to do is take the fully contracted terms, forget about all the rest, because they're going to be 0, and you only care about the fully contracted
אבל
terms.
זה גם רק expectation value on the vacuum, זה נכון?
Yeah, vacuum expectation value.
ואם אני כאילו רוצה לעשות את זה על מצב אחר...
And you're screwed.
כן, ממש.
Sorry. Okay, so let's just show that this works. Or maybe not. Let's show that it works, and you can do the proof. Huh? It's going to be fast. Don't worry. Maybe not that fast. It's going to be quick. We're going to take this state, okay?
אני שואלת.
And let's apply Wick's theorem to this same example that we saw in the beginning. Right, so let's do this. If you're using a computer, what you can do is take this, you copy paste 10 times. right? That's what I did when I prepared this. But now I can't do this. So we have A, K, A, L dagger, A dagger, M, A, N. So the first term in the Wick's theorem is just the operator itself. But note I have now a normal order of all of this, right? And now I have to add the contracted terms. So the first one will be A, K, A, L dagger, contractor. This will take a while. Let's just take the relevant terms, okay? Something will be relevant in a minute.
זה עוד לא הוכחה, נכון? זה עוד לא הוכחה שלך.
No, I'm not going to prove it today. Let's do this because I think it's important to see how this works. Because why is it confusing? Beforehand we had 2 terms, right? And now we have like a million terms. So how's this the same thing, right? That's basically what the question I'm trying to ask. I'm trying to answer.
Because all of them are zero.
Right, that's exactly what's going to happen. A dagger, A, M dagger, L, A, N plus A, K, A, L dagger, M plus A, K, A, L dagger, A, M dagger, A, N. I'm getting there. And then there was the fully contracted terms down here, okay? So we'll take the contractors one by one. So I've done the first pair, I have this one, I have this one, and then this one, and this one, and this one. And now you can use the fact that if they're already in normal order, the contractor is 0. So this is already normal order, right? So it's going to be 0. This is...
Why is it already normal order?
The contractor itself. This part is normal order.
Why?
זה לא normal order.
This part.
זה לא.
Ah, sorry, I'm confused.
No,
You're right. Sorry.
בגלל שהחלק השני הוא normal.
Yeah. A-K-A-L dagger. Okay, so this is not normal order. This thing is, or other way to think about it, the commutator between...
No,
this is not.
הם אפס בגלל ש...
Sorry, this is not either. This is. Right? And the other way to think about it is that the commutator between AK and AN is 0.
Wait, why aren't the first 2 terms not in normal order?
Because you have the annulation before the creation.
Right, because you have an A and then an A dagger. And also you have first A.
No, but it's a number.
No, so the contractor, right? The contractor, right, is equal to 0 only if they're in normal order, and otherwise it's equal to the
number.
Right.
It's a number times A dagger times A, so it's normal order.
No.
This
This entire term is equal to 0. Why? Because the contractor is 0.
Okay.
Here the contractor is non-zero.
Oh, the term is 0.
Right? And the same thing here, and the same thing here, and the same thing here. And the same thing will happen for all these terms. And then these 2 terms are exactly what we had before. So you see it's exactly the same thing, and you now have a recipe for how to do it. That's basically what Wick's theorem tells you to do. You can now that we have shown that it works for the case of 4 operators, you can by induction show that it works for any number of operators. Not now. Okay, questions?